ask questions thinking that it's a stupid question, but no question is stupid. No question is stupid. Every question is a question that can be asked because it doesn't make sense. It's all we are dealing with life and death. So when you're dealing with life and death, no question remains stupid. Everything you should be asking because that's how discoveries came in. In fact, the most smartest people on the earth, have been those people who ask questions. Most smartest people on the earth. I mean, you might ask 100 questions. Nothing will matter if you ask another question more. Nothing will happen. You will only gain knowledge. You've got to ask questions. And that's how discoveries came in, These questions were asked, and then with that discoveries came in, and with that is when all these advances of mechanical ventilation came in. Now there are two industries that are there, and it's impossible to keep pace with that. One industry is medical research. The medical research is such a phase where on an average day, just taking one subject, there would be more than 100 papers coming in. There are more than 100 papers coming in. That's the speed in which medical research is coming. And the second industry that is actually putting up a lot of stuff is the industry. What does the industry do? The industry comes up with every now and then something new. So you have to keep in pace with research and the industry if you really want to go ahead. Okay, the ultimate point is nobody can go ahead of research and nobody can go ahead of industry. But you should be able to find a method and analysis of the way you're going to do it. Okay, you cannot depend tomorrow on Dr. Sanjay talking to you. Tomorrow you have to come to a conclusion as to what I'm going to read so that I can be in tune with what's happening, in sync with what's happening. Similarly, industry, a very important partnership. It's important for you to look at the industry because every now and then comes with new and new advances based on the research. At the end of the day, what do? They try to save lives. At the end of the day, the entire thing is to save lives. That's what we normally do, to save lives. Okay. And mechanical ventilation can be very, very dangerous. It can kill per se. But what exactly do you want these machines to do? If there's any machine in the ICU, especially mechanical ventilators, there are a few things we want to do. We want to ensure that the patient is oxygenated well. We want to ensure that the patient is ventilated well. That means the carbon dioxide removal is okay and safe. We want to do it absolutely safe as possible. We want to make it as much safely automated. When I say automated, means it does whatever we want to do itself. We want to make it automatic because that's what kind of helps everything. We want to make it automated. The other thing is it has to be really, really comfortable, and that's what you see from the start till now. It was controlled mechanical ventilation, which was very, very uncomfortable. As I told you, if he wants to breathe, he cannot breathe because the valves are closed and it is air hunger coming in and it is causing a lot of upset and he is forced to paralyze patients. Correct? From there, we have come to trigger, to things which have made it more and more comfortable, to flow restriction, flow changes. All those things have come in, which is actually making it comfortable. We want this to be as comfortable as possible, and we want to most importantly reduce the work of breathing. The entire premise of doing mechanical ventilation is to not oxygen ventilate only. The entire premise is to reduce the work of breathing. When you reduce the work of breathing, that is when a person starts getting better. The entire attempt for a person who is critically ill is to breathe. And to do that breathing, it spends a lot of energy, these people. And that energy is what translates into lactic acidosis, cytokines, all the nonsense that comes in, that's what comes in. So that's why when they are fighting to breathe, you must be able to support that and reduce that work of breathing. And that is the reason we want to ventilate our patients. So if you have a patient of multi-system organ failure, the reason is not he's in respiratory failure or an oxygen that is going down. The reason is I want to take away his work of breathing because the rest of the work let it go to actually perfuse the organs. You're getting the point. The work of breathing is very, very important. So you can't say the criteria to intubate remains a drop in oxygenation or an increase in carbon dioxide. It doesn't work like that. The criteria should be first and foremost reducing work of breathing. That is a foregone conclusion that if the hypoxia is happening or CO2 is going up very, very high, you need to ventilate. But otherwise, the entire attempt is work of breathing. He's reached that phase because you haven't tackled the work of breathing to begin with. He's reached that phase where the carbon dioxide has gone so high that you have not tackled that particular earlier place. Similarly, he's gone into that severe hypoxia because you have not tackled it earlier. So the entire point is you have to tackle the work of breathing and importantly take the patient off the ventilator also. That should be one of our goals. So that means to say whatever we are doing is going to harm the patient. For example, we are converting the breath from negative pressure to positive pressure. It's not simple here. Your brain is suddenly realizing that when I'm breathing it's coming positive. When all this while in my entire life, when I'm breathing it's negative. Suddenly it's completely changing to something that is so unaccustomed to the patient. So the liberation becomes more difficult. You got a point? And that's the reason that we want to liberate these patients as quickly as possible. So we will want to liberate these patients as quickly. So when you start thinking of liberation, the moment you start putting the patient on the ventilator, the moment you start putting the patient on the ventilator, you start thinking of liberation. Am I going to liberate him quickly? The other point, liberation is very, very important. When we do weaning, we'll discuss about that. Okay, there are certain workhorses that we've been using for time immemorial. You have volume control, you have pressure control, you have SIMV, and you have pressure support. This mode SIMV, as I told you, is now probably we're not using as much. But we are using volume control, we are using pressure control, and we are using pressure support. They will remain our workhorses. If I don't know anything, these are the three modes I should know by heart per se. And that's what we did some time ago. We understood volume control, we understood pressure control, we understood pressure support. But then, as we go ahead, we can't stop by just looking at all of these things, because there are many other modes that are coming in place. There are so many modes. You say PRVC, AVAPS, VSV, Smart Care, PAP, APRV, NAVA, ORVO, ACE. So many things are there that you must understand this, because as I told you, medical research throws you more stuff that comes in which will make it more and more comfortable, and you can't go back to what you were doing in Jurassic ages. That's wrong to be done. For example, when you are doing, I will not say I have learned controlled mechanical ventilation, so I'll put the patient on CMV. We've all changed. We've come to trigger, we've started assist control. But the point, similarly, as time goes, you have to go back to that. You have to go back to understanding what these newer modes are. And only when you understand these newer modes will you actually prosper. So what we'll do is, for today, we will actually cut that particular newer mode, only that one, which is the ASV, and we'll talk about that as of now. Okay, what do we want these new modes to do? These new modes, whatever these new modes, what they want to do. Now, till now I told you what is normally done on a ventilator. Why do we ventilate our patients? Now, what do we want as luxury for these newer modes? We want guaranteed delivery first. We want guaranteed delivery of a pressure and a volume. We want a guaranteed delivery. I want to control that pressure. I want to control that volume. Very, very important for me. It's one of the prime necessities that I want to do, because I want to do less harm. I want to do less harm, so I need the pressure and I need the volume to be absolutely right. And then I want a mode that will help me throughout the process. I don't want to be there, okay, at any given moment and say, okay, now he's getting better, let me change the mode. Now he's getting better, let me change the mode. I don't want to do that. For example, if a person is getting from volume control to assist control, to assist control to SIMV to pressure support, TPs, I don't want it like that. I want one thing that will take care of the whole thing, and that's called automation. I want to do that. I want to ensure that takes place, because I know when I do that, the patient becomes more comfortable. The patient becomes more comfortable. It's very clear that the patient will get comfortable if I do that. And what is going to happen in these newer modes? There is microcomputer technology, which was not there. Till now, all the technologies that we had in the past were all solenoid valves. Now there is microprocessor technology. There is software inside the ventilator. There's AI inside the ventilator, which is changing a lot of things. And that's why you should understand how this has come. Now, does anyone know what this open loop system is? What is the open loop system? The open loop system is like an ambu bag. Okay, so there is a ventilator, there is a gas flow, there is a patient, there is an airway pressure. Chak, 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 chak. This is open loop system. This is open loop system. You understand what I'm saying? There is an ambu bag. I am deciding what I want to do. Patient has to just listen to what I'm doing. This is open loop system. Correct? There is no feedback. There is nothing. That's like an ambu bag. Okay, that's called open loop system. This means to say I'm going to drive a pressure through my ambu bag. It is going to go. That is going to act like the ventilator. There will be a flow inside the patient, and the airway pressure will change. I am not concerned. I am not concerned. What is happening to that patient? I am not concerned. What is happening to the ventilator? There is nothing in my hand. Okay, I am just going to ventilate my patient. This is called the open loop system. Open loop system. It will be the cheapest thing to do, if you ask me. It's the cheapest thing to do. I mean, if I have open loop system, I don't need anything. I don't need anything. I don't have cost only. If I just tell some person to just keep taking a device and just pressing up and down, up and down, up and down, there is no cost only to the system. You're getting the point. It's like a piston, right? Just a piston. Nothing is coming back. But the problem is coping up. How will the patient cope up with a system like this? It's very difficult. So you end up putting the patient on paralysis, you end up putting the patient on deep sedation, you end up putting the patient on all of these things, and it's a huge problem with respect to coping up when it looks at this. Clear on this? The open loop system. So we kind of do not use the open loop system anymore. These open loop systems were available for a long time. It is still available at certain hospitals. It's kept in the museum, but available just to see, not to be used. Okay, it's not being used anymore, the open loop system per se. I've used it in the past. It was a pain to use it. It was a real pain to use a Mendeley. Okay, it is an open loop system. Okay, that's a cost versus coping up. Correct? Now, What is a closed loop system? We are all dealing with a closed loop system. For example, your flow meter is a closed loop system. What is happening in the closed loop system? I am dialing 4 liters and 4 liters is coming to the patient. That is closed system. That's a closed loop. You getting the point? Closed loop system. I am dialing 4 liters on the flow meter and 4 liters is going to the patient. That is a closed loop system. That means in these patients, what is going to happen? There is a feedback coming from here. My feedback is I am giving you 4 liters. So 4 liters is coming from it. That's the feedback. Correct? So look at this feedback here. So this is the feedback. The patient gives a feedback, okay, and that takes the ventilator. In a ventilator system, this is what is happening. Get the point? For example, I have seen the saturation to be 85%. I have come and I have changed the ventilator and I made it 95%. I have changed the FiO2 to 95%. Okay. So this is now as a feedback gone to the ventilator, correct? And this forms a closed loop system. Clear on this? That's a closed loop system. This is about the closed loop systems. So there are many closed loop systems. This could be at the physical variable of the device. As I told you, FiO2 is the physical variable of the device. Where I said if I change the FiO2, it will change the FiO2 to the device. Or the second is physiological variable of the patient. I saw the SpO2, so I changed it. Two systems over here. You got the point? I saw the SpO2 changing, so I changed it. So it is either acting physical variable of the device or the physiological variable of the device. And in the middle of all these things, we have a clinician. Correct? So what is happening over here? There's a patient, there's a physiological measurement that is coming in, which says, say, saturation for example, and then the clinician takes the call on changing the FiO2 or the PEEP, and the ventilator settings are changed, and the ventilator then gives back the support. This is the closed loop system that we are talking about, where the center is the clinician. This means to say, I will require on an average at least 100 to 120 times that I am going to do this in order to make this very comfortable. Actually, we're not doing it so many times, but you require 120 times, at least 100 to 120 times, because that's how the variations would occur. As we are sitting also, besides the patient, the variation will keep on occurring. You stand with the patient, you see so many variations. You will keep on changing, you keep on changing. That's called as closed loop system with the clinician at the center of the loop. Closed at the center of the loop. Yeah. So patient, clinician, and then the ventilator settings change. This is very time consuming if you ask me. If you really want to do a great job, you'll have to stand with the patient. It's very, very time consuming. It is very labor intensive. You have to be there with that patient. They are all labor intensive, and it needs the full attention of the clinician, which is very, very difficult with the given scenario that you can't be with the patient all the particular time. So it's very, very difficult to have this system per se. So it is important to actually do a different small variation to this, which is called as the physiological closed loop system. So what is the physiological closed loop system? The clinician sets a target. Physiological closed loop system means the physician sets a target. Okay, the physiological measurement is taken from the patient and the target is altered. It only sees the error. So this is like a physiological closed loop system. Now the clinician is not telling anything. Clinician has set the target before only. How it was otherwise, real time is changing. Now what has happened? The physician has said, give so much tidal volume. It has to be in this pressure. This is he has given that. So now based on saturation. So he said if the saturation goes less than 80, give like this tidal volume, give like this pressure. So this means to say the physiological parameter is lended to the ventilator by the clinician, but he is not there actively inside the place, making it less labor intensive. Getting the point? So the clinician here is out of the loop. The clinician here becomes out of the loop, and this is called a physiological closed loop system. What does the ventilator do? The clinician only tells the ventilator, tell me when it changes, when the error comes in. When the error comes in, tell me. For example, the pressure is overshooting, volume is getting limited, like in pressure control mode. It is saying maintain that pressure. Maintain that pressure over there. If the volume is getting limited, please give an alarm. So what is it doing? It is maintaining that pressure. It is looking at the pressure inside of the patient. Maintaining the pressure control of 30, 30, 30. Volume has gone very high. Suddenly there is a volume alarm saying high volume alarm. You understand? So that's called a physiological closed loop system, like this. Like for example, the patient was at a measured ET2 of so and so, and then after some time it has gone down to smaller amount. Then there's a disturbance. This is understand the disturbance. Like for example, there's a small change, it's not going to tell you. But if it's a major change like this, it will tell you. You understand? So it takes the disturbance in place and tells you, okay, this is let's mark that's just a disturbance. It is able to do that. It's going to give you only significant parts of the entire system. You got the point, huh? This is what a physiological closed loop system. And if you really want to have available closed loop systems, there are many. For example, I can have a closed loop system looking at airway pressure and tidal volume. That's how all the advanced modes are made. They are controlled in 2-3 types. So you can either have this, or you can have the ETCO to POCO control, or you can have the SPO to PO to control, or in NAVA you have the ADI, that is amplitude of the diaphragmatic excursion. You understand the NAVA, where the diaphragmatic, so the trigger here is electrical trigger. So it is looking at the electrical trigger and giving breath. Okay, here it is SPO to PO when it is changing. Here ETCO to changing, airway pressure and tidal volume is changing. So there are various ways and that a ventilator can be formed into a physiological closed loop system. Clear? Understood? Each of the advanced modes are based on which variables are actually taking for physiological closed loop systems. Clear on this? Clear till now? Okay, and definitely the era of physiological closed loop feedback control is here. There is no doubt about it, and it is all going to be physiological closed loop control only. There is not going to be any more a situation where there will be no physiological closed loop. There will be physiological closed loop coming. The era is here. Okay, and what do we want them to do? We want them to be safe. When you're doing physical closed loop, it has to be safe. It has to be comfortable again. It has to do its job. Okay, it has to do its job, and it should modify on its own. It should modify things on its own. Then only we'll call it as physiological closed loop. And I think the closest to a physiological closed loop will be ASV. Closest. The closest. Okay, there are many, but I feel the closest is probably the ASV. Because normally what will happen if a person is getting intubated, you first put him on a controlled mandatory ventilation, then he'll start triggering the ventilator to become assist controlled ventilation. Then from assist controlled ventilation, you'll slowly reduce the rate, and then you may want to go to SIMV or go to pressure support. From pressure support, you'll go to TPs, and from TPs, you'll extubate the patient. So you'll have 5 major things you're doing in the middle, and in those 5 things, you'll be altering the ventilator maybe 10-15 times. So totally 10-15 times you're going to alter 5 times, 500 times you're altering the ventilator. You're getting the point? That means the amount of times you're going to change the ventilator. But what happens with the ASV now? It's just one mode. It is just one mode. There is no multiple modes. There is no pressure support. There is no right from start to the end till extubation. There is only one mode. There is only one mode. So that now helps me that it has removed one of the part from my story. It's removed one of those parts where I have to change modes. Okay, so it's modifying itself. And how does it do that? Normally, if you have pressure control, CMV, SIMV, pressure support, we are doing a lot of alterations and a lot of things over here. Correct? Many buttons we are pressing. When you're looking at volume control, pressure control, SIMV, we are pressing a lot of buttons. We just discussed that. Okay. Now what happens over here is the entire ventilation mode over here is ASV. Okay, CO2 elimination is one thing and oxygenation one thing. The ASV is the mode. It is all these modes together. Okay, the CO2 elimination is completely based on percentage minute volume. It's completely based on percentage minute volume. Percentage minute volume on an average is 0.1 liters per kilogram is your percentage minute volume. Okay, and your oxygenation is based on PEEP and FiO2. Okay, this is what is ASV. This is only 3 settings you have to press. This setting, and this setting. There is no other settings you need to press. The ventilation mode, which is responsible for removal of carbon dioxide. Okay, the CO2 elimination, which is what it is. Oxygenation is PEEP and FiO2, and you just press ASV. These are the only settings you require. Okay, so let's understand this. It's not what it is exactly. It is actually a volume guarantee. Pressure controlled ventilation. Now, how does it do that? It does it very intelligently. It does the whole thing not by just giving you a guaranteed tidal volume and guaranteed pressure. It does the whole thing by changing the respiratory pattern. The whole pattern itself is changed. It changes the respiratory pattern. When I say pattern, what is it changing? It is changing the respiratory rate. It is changing the tidal volume, and it is changing the I ratio. It is doing everything. It is changing the respiratory rate, the tidal volume, and I ratio. The question is how. The question is how does it do it? The question is how does it change this RR? How does it change the tidal volume? How does it do the I ratio? How does it do this? I mean, to understand this is a very interesting thing as to how it do it. But I feel if there is the physiological closed loop ventilation, this is probably the king of it, I feel. So, what is an optimal breathing pattern? If somebody asks you what is an optimal breathing pattern, the optimal breathing pattern, first we go back to physiology to understand this first. The optimal breathing pattern is the one that has the least work of breathing and the least pressure applied by the ventilator. This is the optimal breathing pattern. How is the optimal breathing pattern? If the work of breathing is the least, that is your optimal breathing. Clear on this till now? and the pressure applied by the ventilator should also be the least. That means it's your optimal. Okay, so we need to figure out a ventilator mode that will actually give the least work of breathing and the least pressure applied by the ventilator. So let's go to some applied physiology. Okay, this guy is called Lilje Strand. He's from Scandinavian, ACTA Stand in 1954, writing some very old book. This article coming. This guy used to do the article, all the pulmonary function tests on himself only. खुद पे करता था, खुद निकालता था सब values. At that time there was very difficulty in actually recruiting people for examining in the 18th century. So he did all of these graphs, and this is one of the graphs that came in. Now we must understand this graph a little bit. On the x-axis you have the work of breathing, and on the y-axis you have the respiratory rate. Okay, and what he has plotted here is the work of breathing, the total work of breathing, which is usually divided into two parts. It's the elastic and the viscous load. I'll explain to you what these are. Okay, so when you are at a low tidal volume, to maintain a minute ventilation, I will require, when you have low respiratory rate, if I want to maintain my minute ventilation, I will require very large tidal volumes. Simple? Yes. If I have to maintain a minute ventilation, so I will require very large tidal volume. That means my work will be very high. It will be like this. Yes. Then wait for a long time. Then big breath I have to take. So my work is very, very high. That's why if you look at the work, it's very, very high. If the respiratory rate is on the lower side. Clear? And as I go higher and higher and higher, my amount of tidal volume reduces. But beyond a certain time, when the RR is very fast, my tidal volume will be barely 200, 300 or 150. Now my work will become even more fast. I have to breathe really, really fast. You understand? So what is going to happen is when I start my breath at a very low respiratory rate, my work of breathing is very high. And if I go very high on the respiratory rate, again it is going to be very high because I have to breathe very fast. That will be to get the ventilation in. You getting the point?
Correct.
You getting the point? So the work of breathing will go and then go up. Correct? Getting the point? Till now clear? Okay. So let's go to the waveform here. For example, this is what I was talking to you about. This is the elastic work. The elastic work to improve or open up the lung. So if it was very low respiratory rate, you will see that the work of breathing is very high.
Okay.
And as it goes higher and higher, it will start again slowly going up. It will start going up. Correct? So there is an optimal respiratory rate where the work of breathing is minimal. There is an optimal respiratory rate. Okay, where the work of breathing is actually minimal. We don't know what it is. This is elastic. So if we can find the elastic workload, we can actually find the optimal respiratory rate. You getting the point?
Yes.
If we get the elastic workload, we can find the respiratory rate. Similarly, when we have the resistive work, what we know is if the RR is slow, if it's very slow, the amount of frictional resistance is going to be less. You getting the point? The amount of frictional resistance is going to be less in the airway. If I increase my RR, make it faster and faster, the resistance on the airway will be higher and higher. Correct? So in this also, in short, if your RR is 5, there will be no resistance. If your RR is 5. So if the lower the respiratory rate, the least the resistive work of breathing. So you have two works. You have elastic work and you have resistive work. So I need to figure out the optimal workload of the respiratory system where I can balance the resistive work and the elastic work. You getting the point? That's when you start breathing very, very well. That's when you start breathing without a problem. You getting the point? So now, in this case, in this scenario that we have over here, that is the optimal. Correct? If you look at it, it is some elastic workload that it is taking away. It is some viscous load, or what we call that is resistive work that is taking away. And it is getting a respirator of around 15-16. Okay, which is an average that we have. That is the average that we have, 15-16. That's why our average is 15-16. Okay, elastic work and resistive work overcome karne ke liye. Clear? So let's take the example of two extremes. Okay, let's take the example of a person who's got an increased elastic work of breathing. If you've got an elastic increased work of breathing, the RR has to be higher. So if you have a patient very low compliant chest wall, elastic work is very high, the RR has to be high, ARDS. The ARDS, the RR should be high. Don't keep the respiratory rate low because the work of breathing is going to be high. You getting the point? ARDS. Similarly, when there is bronchospasm, the resistive work is high. So when the resistive work is high, you need the RR to be low. That's the principle of having low respiratory rate when there is asthma and high respiratory rate when there is compliance related issues, COPD related issues. This is the physiological basis behind it. So looking at it, you can understand that in this, how the RR is on the higher side, and this, how the RR is on the lower side. The work of breathing, it all depends on the work of breathing. Now what ASV does is this beauty. It actually takes that work of breathing to be the minimum work of breathing. It takes that into proportion. It takes that. It finds out that. And how does it find out that work of breathing? It finds that work of breathing by a combination of two equations. It does two equations. One is called as the Otis formula and the other is Beach formula. Again, at that time, 18th century, the formulas were made for work of breathing. So they looked at those formulas, and then they put a very important part into this. Put these two common elements together, which is the common elements is a dead space ventilation and the RCEXP, and we'll come to what that is about. It puts those two formulas together and then tells us which is the minimum work of breathing, and then ventilates that. How does it do that? Okay, how does it do? You first define the target. It first defines the target as the ideal body weight, which is calculated from the patient type, gender and height. That is why if you don't put the ideal body, if you don't put the gender, type and height together in a person, it will not be getting the ideal body weight. The first thing is to get the ideal body weight. So if you start the Hamilton C6 ventilator, the big ventilator that we use, in that ventilator, if you do not set this right and this right, it will not be able to do its job the right way. So the first thing as a doctor, the nurse will not know this. The nurse will not know this. It's very important for you to check whether this has been entered inside. It's very, very essential. Okay, because it needs those numbers to understand further. And then we add a percentage minute volume. It is a percentage of the normal ventilation. For example, 100% means it is calculating this as 0.1 liters per kilogram. This is 6 liters minute ventilation for a 60 kilo individual. You getting the point? So 100%. Getting the point? So when I say 100%, means it's what you're going to give to any person who's breathing normally. If the person is acidotic, you require higher. So if the higher means 120%. So it is expressed as normal ventilation, percentage of normal ventilation. This means to say if the person has higher minute ventilation when he's having acidosis, fever or things like that, you need a higher minute volume ventilation. If it's lower, if the patient is weaning off, you may require lower minute volume ventilation. Samajh mein aa raha hai? That's a percentage minute volume. It is set by us based on patient condition and PCO2 counters. So I'll explain to you how. Okay, how do you set that? Okay, so it looks at both of these things and gives a target minute volume. Okay, if we're looking at percentage minute volume, there's a target that is decided, a target minute volume. Okay, and that is defined by the clinician, sir. Now, what does it do? You assess. So first thing is you define the target minute volume. This we just discussed now. How do you decide the target minute volume? So percentage minute volume will be 100%. So if the patient is very, very tachypneic, acidotic, probably I don't want to use an ESV because it's just too much. We don't know how much to do. Okay. So on an average, 100%. So if the patient is having fever, it should be 120%. If the patient is not having any fever, 100%. 100% means it will take how much minute volume? 6 liters. If it is a 60 kilo individual. Correct? What I'm saying? And then it actually finds the PASV limit. That is a pressure limit that it is going to limit to. We'll come to how it does that. So it decides a pressure limit. How does it do that? We'll come to that. Okay. And what it does over there is it gives first 3 test breaths. How does it decide that pressure? It takes 3 test breaths. And with that, it calculates the inspiratory pressure, the total frequency, the total inspiratory time, and calculates something called as RCEXP, compliance and resistance. It looks at all of these things. So it looks at RCEXP, it looks at compliance and resistance, spontaneous activity and tidal volumes. This PASV limit, the highest pressure it can go, is limited by this highest pressure that this can go, that the tidal volume can go, is limited by this equation. It's a deep dive, a complete deep dive. So the tidal volume highest will go as 10 into dead space. It calculates the dead space is 2.2 into ideal body weight. Okay, so that's your dead space, 2.2 into ideal body weight. So initial ideal body weight देख लिया और उसका 2.2 into ideal body weight 60 अगर है तो 2.2 to 60 1200 ml would be your maximum tidal volume it can go up to. You understanding? Similarly, this PSV limit minus PEEP into compliance. It will look at the PSV limit that we have set, P limit on the ventilator is called P limit. It looks at the P limit and into compliance with the maximum tidal volumes, or it will look 1.5 into high VT limit. So it will either look at one of these, whichever the smallest. Whichever the smallest they give. If it has to increase the tidal volume, it will look at all of these things. And lowest will be 4 into ideal body weight. The lowest will be 4 into ideal body weight. That's why the ideal body weight becomes very important for you. Lowest it can go is the lowest is 4 into ideal body weight. Itna samajh mein aaya? How it sees the highest, how it sees the lowest. That's the defined limits beyond which it will not do that. Okay. And the PSV limit also, it will depend on something called as high pressure limit and VT high limit. So whenever you are actually looking at that ventilator, there will be two lines that come. One is a blue line and one is a red line. The blue line is 10 below your P limit. That's your PSV limit. This means to say, if I set my P limit as 40, the pressure at which it can go highest will be 30. समझ में आ रहा है?
No, sir.
नहीं समझ में आ रहा है. So it has to give some pressure. We want to guarantee a certain pressure of a certain volume, and I want to ensure that the pressure does not go more than 30, because if I go pressure more than 30, I'm going to injure the lung. 30 is like the plateau pressure which I want to keep at. Correct? So I'm going to tell this ventilator that don't go above 30. For that, how do I know it is not going above 30? Because I set my P limit at 40. So if I set my P limit, my high pressure limit at 40, it will not go beyond 30. समझ में आ रहा है मैं क्या बोल रहा हूँ? So I know that, so I have to set my P high limit. If I don't set my P high limit, my PSV limit will not be set immediately. Getting the point? P high limit. So P high limit is very, very important in these cases. So first it gives 3 test breaths, and then it calculates compliance, resistance, and something called RCEXP. How does it find the maximum respiratory rate? This is how it does the maximum respiratory rate. It's a very deep dive. This is very deep dive. Maximum respiratory rate, how it finds? It does this equation. Either this or this or this. 20 divided by RCEXP or target minute volume divided by minimum tidal volume. This is the maximum RR it will go up to. The minimum RR will be 5 breaths per minute. So this is a formula which will tell you which is the maximum RR and which is the minimum RR. Okay? This is how it basically tells you how to calculate the RR. Now let's understand RCEXP. The most important value when you're looking at ASV is RCEXP. Okay, now what is RCEXP? RCEXP is the time constant. Now what do you understand by time constant? This is what your time constant is all about. Okay, you have inspiration, you have expiration. Okay, the amount of time it takes for the volume to get out of the lung is called as time constant. Okay, so if you look at this, it takes 3 times for complete inspiration, 95%. 95%. This is inspiration, this is expiration. It takes 3 times the time constant normally for the patient to completely exhale, to remove off the ventilator or completely send the volume inside. Clear on this? So exhalation is very important passively. So if passive exhalation mein, it needs 3 time constant to completely exhale. You getting the point? So the entire point is it actually figures out what is your time constant. So by figuring out a time constant, it now knows what is your expiratory time. You getting the point? This time constant, RCEXP, which is basically a combination of resistance and compliance. It is a combination of resistance and compliance. That's why it's called RCEXP, expiratory time constant. Understood this much? RCEXP? Now let's understand a little bit more about RCEXP. Why do we need to monitor the RCEXP? We need to monitor the RCEXP because it gives us valuable information. So normally the RCEXP is up to 0.6 to 0.9. So on your machine you will see RCEXP 0.6 to 0.9. If the RCEXP is gone more than 0.9, what does it mean? That it is taking more amount of time for it to remove that air. Means either there is a bronchospasm or there is an obstruction somewhere because of which this is going further and further. So on the ventilator you are not seeing peak pressure and all these things. On the ventilator you are seeing RCEXP. So if the RCEXP is gone more than 0.8 or 0.9, it means to say I need to check my tube, check my patient. I need to check to see what is, because it's somehow going to give what it will do, because clear on this? Clear on this monitor? So say for example you have a patient in which you have said maintain pressure at 40, 30 for example, and now there is going to be a bronchoconstriction. What it will do, it will see that as bronchoconstriction and think from that work of equation and that whatever we talked about physiology, it will think that I have to reduce my RR and I have to increase my tidal volume. So it will increase my tidal volume, it will deliver that breath, whatever I have to deliver that breath, but the problem is obstruction. Are you getting the point?
Yes.
So RCXP is similarly, if it goes low, it means the lung is getting stiffer. The lung is getting stiffer. Your compliance is going down.
Same like minute volume that alarm is coming, no? In ventilator, normal ventilator. So RCXP is like.
No, not at all. RCXP is a physiological variable, time constant. No ventilator will give you time constant. This is time constant.
Mechanism is almost same, like if it is high or low, kind of RCXP is also doing.
No, it won't be like that. It won't be like that. So if a person gets bronchospastic, what you'll see on the ventilator is the peak pressure going up. If the patient has got a tube block, the peak pressure will go up. Whereas here it is not going to be like that. Here what is going to happen? Peak pressure is not going to go up because you have set a PSP limit. वो देता रहेगा, tidal volume increase करता रहेगा. Okay, but what you have to see is RCXP. Getting the point? Understanding? So if I put this clearly, you have to monitor it. Okay, it's important to measure it also because as a treatment modality you can use it. For example, you have one bronchodilator, you have a patient who is bronchoconstricted. Do nebulization till it comes back to normal. Do remove the king of the tube. Remove the secretion of the tube, will become normal. In your case, remember RCXP was 0.9. Okay. So
how in stiff length the RCXP will go down?
What? Sorry?
In stiff length, it will go down. RCXP.
Correct.
How sir,
Because now if the lung is stiff, okay, it is taking more amount of time for it to inflate, less amount of time to inflate because tap karke andar baar aayega wo. It's not expanding only. Normally what is happening, your lung is expanding nicely, na? There is no expansion only here. So the one tap karke pressure बंद हो गया ना, खत्म हो गया pressure, उधर ही full हो गया. So it tap करके मारा जाएगा वो. Got the point? So in short, you have three interpretations here. One interpretation, this is normal, 0.6. So on your machine also you have an interpretation. If you put the lung window, there is an interpretation that looks like this, 0.6 to 0.9. There is an interpretation that looks like this, where there is a small triangle that comes over here. Like a hexagon that comes over here. It says that there is stiffness in the lung because less than 0.6 RCXP has become. And then the final is, there would be bronchospasm. That's why you see this small red thing coming inside. You getting the point? So on the ventilator only you can see it. Of course, the numbers you should know. But the numbers say if it's more than 0.9, look for bronchoconstriction, look for tube block, look for kink, look for all those things. What will be happening is very different. We'll come to that as to what will happen. This is the interpretation of this entire thing. So you got us this much. So by setting my ideal body weight, I have set my P and I am setting my P limit. I have decided what to put up over here. I have set my, it gives 3 test breaths, finds the compliance, resistance and the RCXP from that. Compliance, resistance and the RCXP. And based on that, because now it knows the RCXP and 3 times the RCXP is your expiratory time, it sets your I ratios. And it does this breath by breath. Each breath, next breath. This breath, next breath. It keeps on doing it breath by breath, from patient breath by breath. And it sets it by using the ASV algorithm. That's what we talked about. The ASV algorithm that we talked about. And then based on that, it adjusts the mandatory rate and the P inspiration. Based on that. It also changes the P inspiration. That means we have set a limit. For 20 jana hai, ki 25 jana hai, ki 30 jana hai. It will base that entirely thing on this and give you that P inspiration. So the P inspiration may keep on changing on your ventilator. Your P inspiration will keep on changing because it is adjusting to give that tidal volume. How does it do that? Also, we'll come to that again. Okay, how does it do that? Clear on this till now? So it's a closed loop control if you see. Why is it closed loop? You have only set an ideal body weight and a target. What else it is doing? It is doing everything else. It is setting your RR, it is setting your tidal volume, it is setting your I ratio, it is setting your pressure, and it is guaranteeing a pressure, guaranteeing a tidal volume, guaranteeing a minute ventilation because you have put a set of minute ventilation also 100% of the ideal body weight. You getting the point? So it's doing everything. Okay. So how does it do it? So target minute volume, how does it find out? If it's a passive, so how do you adjust the target minute volume? That was the question that we're talking about. So we start on a starting point. You can start if you set the ideal body weight, age and gender properly. You immediately put it at 100%. You put it at 100% because you know you want to give 6 liters. So you put it at 100%. समझ में आ रहा है till now? You put it at 6 liters. Now, if it's a passive patient, and after say 15-20 minutes you are finding high EtCO2, simple, increase the minute ventilation by how much? By 10 to 20%. Increase by 10. So if it's 100%, make it 120%, and check after some time. After some time means after 10 to 15 minutes. Correct? After some 5 to 10 minutes, not even 10 to 15, 5 to 10 minutes, you can check it again. Clear? But in this, there's not going to be flow restriction and all that nonsense that happens otherwise. Normally, what is happening? If you increase the minute ventilation by increasing tidal volume and RR in your ventilator, there is going to be flow restriction. There will be auto peep development, and all those things will come in. Here, those things will not come in. Okay, because it is setting the I ratio in such a way that the work of breathing is coming down. Okay, so you will increase ventilation. Similarly, with the low EtCO2, I will reduce my percentage minute ventilation. Clear on this till now? Clear on this? Simple. For a passive patient, very simple. What happens for an active patient? If you see an effort or an increase in the RR, that the RR is going really very high, and the effort is, you can see an effort on the patient, then you increase the minute ventilation. Percentage again by 10 to 20%. If they reduce RR or high PS, reduce minute ventilation, they are probably going to move off the ventilator. Clear? The 100% should not go anytime more than 300%. It should never go more than 300%. Okay, if less than, and try to keep it less than 100% in chronic hypercapnia and hypothermia. In chronic hypercapnia, when you have the carbon dioxide to be on the higher side, don't start at 100%. Start at 80% or something like that, because you want that to be on the lower side. Clear? So good starting points you've understood. For minute ventilation, how to adjust it. It's very simple, but you have to adjust it properly. Clear?
Sir, you said if there is an obstructive pathology, increase the minute ventilation.
No, we don't do it.
The machine does.
Machine will do whatever it has to do.
You are saying that in chronic hypercapnia, we are keeping the setting only less than 100.
We are keeping the minute ventilation only less, not the tidal volume and RR. That they are deciding. It is deciding the tidal volume, it is deciding the RR. We are only saying that total minute ventilation, which is normally in you and me at 6 liters, in him it will be only 4 liters. So we are keeping it at 4 liters. Okay. But the tidal volume and the RR is being managed by, is being changed by the ventilator. You are getting the point? You understanding what either others I would do if there's a patient of chronic hypercapnia and the patient is in the ICU? What I will do? I will put the ventilation. I will reduce the FiO2. I will reduce the RR. I will reduce the tidal volume. I'll increase the tidal volume slightly. So I'll do all of these things manually. I'll look for peak pressure. Look for auto flow. Look for whether the patient is having breath stacking. Look for trigger. I'll do all of these things. Right? I'm not doing anything here. You get the point? I'm only adjusting minute ventilation. Clear?
So one more doubt. As you said, we are gonna set the pressure already, right? Now
we are setting only the limit of the pressure.
Yeah, limit of the pressure.
So when you set a limit of 40, the PSA limit will be 30.
30.
That is what you see the blue line and the red line. You see that on the ventilator you see 2 lines on the pressure graph. The lower line is the PAFC limit and the top line is the P high limit.
So now in the first case, when the patient is passive, high EtCO2 is there. On normally ventilation, if we increase the RR or the tidal volume, we are creating an auto peak.
Correct.
Right. Then why there will be not an auto? Because
this is monitoring. When it goes up, why you're getting an auto peak? Because you have not set the I ratio, the expiratory time you don't know. You are looking at the waveform.
So everything
this is changing all RR, I, T, TV, everything is changing in such a way that the work of breathing comes down. That's why I said that physiological work of breathing with respect to the elastic forces. I showed you that graph where the elastic force, viscous force, resistive force, and work of breathing. It actually looks at that graph by looking Otis equation and mean together and generates that particular I ratio. So beauty of the ventilator is that. So that's how it does a target. So how does it define the target? For a given target minute ventilation, say I put 100% for a 66 kilo individual. Okay, what will be my target minute volume? It will be 6.6%. I have set minute ventilation 100% for 66 kilos. So it is taking 0.1 liters per kilogram and saying it is 6.6 liters per minute. This is what it is seen inside. ये आपको दिखता नहीं है, लेकिन अंदर है 6.6 liters because you have said 100%. Correct? And that's why you are seeing this graph. It is showing our resistance compliance. So it first gives 3 breaths. In that it already decides that there are combinations. There are combinations here of tidal volume for this target minute volume that is there throughout. High tidal volume, low RR, low tidal volume, high RR. Just how we discussed. You discussed that whole graph, where there is elastic work and resistive work. So now it finds an area which can be infinite, right? From 1600 tidal volume up to 60 respiratory rate. which will give us 6.6 liters per minute, because this is tidal volume into RR.
Correct.
समझ में आ रहा है? It just creates that graph first, and we have put the limits. We have told the limits. We have told the, we discussed the limits based on ideal body weight into 4. It would be the lower limit for tidal volume, and then P ASV limit minus compliance minus P upon compliance would be the high tidal volume limit, high pressure limit, high tidal volume limit. So we discussed all of those things as to how it decides those limits, those Swan equations that I showed you. With that, it knows the limits over there. Correct? Now, what does it do? The optimal it finds. After looking at the compliance, after looking at the resistance, it finds the optimal, and that's the optimal RR and optimal tidal volume based on the respiratory resistance and the compliance. Here with the compliance, it finds the optimal from that Otis equation. Okay? And then what it does, it defines that limits. So it says, do not go below this. That's the limits we discussed. That don't go below this tidal volume, because if you go below this tidal volume, you are ventilating dead space. We said if you're going to go below that to a certain number, it will have to be very, very fast, and that work of breathing will go up. So it goes to that tidal volume, which is called, which prevents it from going to that dead space ventilation. You understand? So it defined that limit of dead space. Clear on this? So it says, do not go beyond tidal volume of say 375 here. It said that. So it is not going to allow the patient to be ventilated on a dead space. Clear? The second thing it does over here is to actually put the alarm for the RR to prevent what? Apnea. So it's preventing apnea here. It's preventing apnea here. You're getting the point here? It's preventing apnea here. So there is no more apnea. It says don't go. So what was our rate? 5. Remember 5. 5 was the apnea that we had defined limits as 5. It defines it as 5. So it's defined as at 5 over there. Then it also looks at the P limits that we've set. We've said by 30 is our P limit we have set, means 20 is a PSV. Or if you have set P limit as 40, the PSV limit is 30. So it sets that and do not go over that limit or that tidal volume, and gives us barotrauma there. Prevents barotrauma there. You understand? It set that limit over there. And then it also puts a limit over here which will prevent autopy. So now it gets a window to ventilate this patient by varying the pressures and generating that particular tidal volume. Now it knows that these are the tidal volumes that I must use, and this is the RR that I must use. Clear on this? It knows that. So once it defines a target, the next thing is it puts that safety window in place, which looks something like this. So on the ventilator, it looks like this. On the ventilator, it looks like this. That's the safety window it's creating. Again, remembering, this is apnea, this is dead space ventilation, this is autopy, and this is barotrauma, volutrauma. So it has created a safety window, and this is called as a ASV window. So if anybody asks you what kind of window this is the ASV window. Okay, it is the ASV window, which is also called as the safety window, that is over there. And what does it do? So it puts the patient as a point, as a plus. So it looks something like that. The patient is seen as a plus as to where the patient is, and then depending on how the patient is moving, for example here it will reduce either the inspiratory pressure or reduce the RR to get it to closer to the optimal. So it tries to get it to the optimal by changing the P limits and the RR. You getting the point? So it keeps changing the P limits and the RR because we have put a PASV limit to that, under that limits, and get the patient back into that particular point. समझ में आ रहा है? It keeps doing that breath by breath, breath by breath, breath by breath. The moment it comes here, it will try to move it back inside. Get the point? So it keeps doing that on a regular basis, and thus maintains this patient at that optimal. For example, if it's on that region, it will increase the pressure, increase the mandatory respiratory rate, because it has to move this here. It will move the RR. It will increase the pressure, so it comes in over here. So it keeps doing that on a regular basis, so that it remains in that zone where where their work of breathing is the lowest. It's optimal work of breathing. And this means if it's a wide square-shaped safety window, it means this is normal lungs. So how will a bronchospastic lung look? How will a bronchospastic lung window look? How will a emphysematous lung window look? Emphysema window में क्या होगा?
Vertical triangle दिखेगा.
Vertical कैसे होगा? Emphysema में क्या होगा? The tidal volume should be lower and the RR should be higher. So it will not be vertical, it will be horizontal. So if it's so it will find out the emphysema and create.
Vertical, huh, sir?
No. When the person is having a stiff lung,
But there are more dead space.
when the patient has stiff lung, when the patient has stiff lung, the time constant is low or high?
Low.
It's low. So when the time constant is low, you need a higher RR. Get the point? When the time constant is low, you need a higher RR. And when you get a higher RR, the tidal volume has to come low. So that's why you'll have a low tidal volume and a high RR. Here. So in the stiff lung, that's what the ARDS lung is, right?
COPD will be vertical.
So ARDS lung will be like that. What about obstruction? In obstruction, this is what it's going to be. In obstruction, what is going to happen? The RCHP is very high. Since the RCHP is very high, I need large tidal volumes and I want very low RRs. So when you see a window that looks something like this, because of very high time constants, it basically means there is bronchospasm happening. At that stage, the RCHP will change. Okay, for example, look at this. The RCHP here is 2.45 seconds, much higher than 0.9. Okay, similarly, when you go backwards, this is the one you see RCHP is 0.18 seconds, which indicates that it's a stiff lung. You get the point? It's a very, very stiff lung. Low compliant lung, not high, low compliant lung. Clear?
Yes, sir.
You got the point? So by looking at the window, it creates that window. So that's why you as a bedside doctor should look at that RCHP regularly. क्योंकि अगर समझ लो RCHP has gone very high, this thing will consider it to be because of, say for example, it is RCHP has gone high because there is a clot in the tube or there is a block in the tube. It will go high, no, because there is an obstruction.
Right.
So if find an obstruction, this ventilator will think that there is bronchospasm. What will it do? It will make this window. It will make this window. Which it will make this window. It will reduce the RR and it will increase the tidal volume. You understand? So you have to be certain by looking at the RCHP and treat the cause there. You understand? So when we teach somebody in the ICU about what monitoring to be done in a patient who's on volume control mode, we will say look at peak pressures. Because peak pressures and plateau pressures give us the answer of what the lung is looking like. Here we can't say peak pressure, plateau pressure. It's like a pressure regulated volume control mode. So when it's like that, volume guaranteed pressure support, you will need to actually figure out the RCHP. Because the volume is also changing, pressure is also changing. What do you see in that? You're getting what I'm saying? So the RCHP is the only one you can see in this case. That is why if you have a patient who is on a tracheostomy and there is leak coming from outside, again it will create problems. The RCHP will keep on changing. Okay, if there is leak around the airways, it will not be able to pick up that properly. So that's why this is not a mode when it comes to bronchopleural fistula, when it comes to pneumothorax. It's not the mode to be used. It doesn't make any sense to use this for any of those things, because if there's a slight leak also, it will actually think that there is something else happening and change the entire dynamics of the lung. It will not work only. It has to be watertight. If that leak, airtight, watertight has to be. If that leak comes in on the ventilator, it will perform very differently. You're getting the point what I'm saying? There should be no leak. Okay, very, very important. So how do you wean them? So step one for this procedure would be, if the actively breathing patient is there, if he's actively breathing, just reduce the minute ventilation to 70%. Reduce the minute ventilation to 70%. 100% pay, make it 70%. Make it 70%. Step two is look at what is happening there. This is now the patient, right? So is the breath rate less than 30? Is the P inspiration less than 15? Because pressure support में 15 से कम होना चाहिए. P less than 8 है क्या? Oxygen. This is usual criteria. P less than 8 and oxygen less than 40%. This is our usual criteria. But this is what you're looking here. P inspiration less than 15 and breath rate of less than 30 breaths per minute. When that occurs, convert the P to 5, oxygen to 30%, make the minute ventilation to 25%. And that would be the SBT here. That would be the SBT here. You getting the point? You convert this to 25% minute volume, percentage minute volume, okay, which is very minimal, 1/4 the rate, maybe a liter, and do it for 30 minutes. If the patient does this for 30 minutes, take off the patient from the ventilator. You're getting the point? So, SBT is sponge breathing trial. So the sponge breathing trial in this ASV mode for weaning would be something like this. So don't convert from minute ventilation ASV to spontaneous. You don't need to do that. You're getting the point? You don't need to do that. From ASV to spontaneous, ASV just reduce the minute volume to 25%. You are in weaning already. for 70 and then for SBT 25%. So this is how you basically go for weaning these patients. You getting the point? So if you ask me, if I add on to that carbon dioxide and SpO2, it becomes a real physiological closed loop ventilation. The real one with everything. You understand? At this moment, we have only put the RR, we have only put the tidal volume and the IE ratio with the RCE XP coming in. Correct? So that's how the physiological closed loop is coming in. But if you really want to make it more physiological and extremely intuitive, then I'll add SpO2 and EtCO2. If I add SpO2, EtCO2 and define a target, if I define a target, it will do that also. Because as of now, what I was adjusting PEEP, FiO2 and minute ventilation. These were the three buttons I'm pressing. I'm pressing PEEP, I'm pressing FiO2 and I'm pressing minute ventilation. Correct? Minute ventilation is looking after the carbon dioxide, PEEP and FiO2 looking after oxygenation. Now if I tell him that I'm giving you SpO2 and I'm giving EtCO2, it will take care of that also. And that is what we called as IntelliVent. Where I don't touch anything. I just connect the patient on the ventilator. I just connect the patient on the ventilator and I ensure that the saturation probe is there and EtCO2 traces them. So get to the point. There I don't do anything. Everything is done by the ventilator itself. Even this change, so in that way, IntelliVent, what will happen is, if my ventilation is coming down to 25%, it will perform the SBT itself. Otherwise, if it come from 100% to 70%, 60%, it will then check, is everything falling, is all these falling in place? If all these things are falling in place, what it will do? It will go to the SBT by going to 25% minute ventilation. Because on its own it will do that, and then it will extubate the patient. It's right to extubate. Are you getting the point? It will do that itself. Okay, so that's why I feel, the closest to this is the real PCLC. I feel for certain. Automation is definitely magic, and ASP is closest to magic, is what I feel, frankly. But there is more to do on this. I think we'll break for now. Any questions now on this?
The role of sedatives